Hello everyone. Today we will discuss about degrees of freedom of mechanism. So take an example of a rigid body in space. Now this rigid body, it can translate along x direction, it can translate along y direction, as well as it can translate along z direction. Along with this rigid body can rotate about x-axis, it can rotate about y-axis, as well as it can rotate about z-axis. So we can say that an unconstrained rigid body in space has 6 degrees of freedom. Unconstrained rigid body in space has 6 degrees of freedom. Three degrees of freedom are for translation along x, y and z axis, and 3 degrees of freedom are for rotation about x, y and z axis. We can define degrees of freedom as number of independent motions a body can have. Number of independent motion a body can have. This is the general definition of degrees of freedom. Number of independent motion a body can have. And rigid body in space has 6 degrees of freedom. 3 degrees of freedom for translation and 3 degrees of freedom for rotation. Now in terms of mechanisms, we can define degrees of freedom as number of independent coordinates required to define the position of each link in a mechanism. Required to define the position of each link in a mechanism. So for mechanisms, we can define degrees of freedom as number of independent coordinates required to define the position of each link in a mechanism. Now there is one more term for mechanisms called as mobility. You can define mobility as number of independent input parameters. Number of independent input parameters that are to be controlled so that the mechanism takes a definite position. So we'll repeat this. In general, we can define degrees of freedom as number of independent motion a body can have. For mechanisms, we can define degrees of freedom as number of independent coordinates required to define the position of each link in a mechanism. Mobility is defined as the number of independent input parameters that are to be controlled so that the mechanism takes a definite position. Now to understand this, we'll take an example of slider crank mechanism. We'll take an example of slider crank mechanism. crank, connecting rod, piston. We'll number the links. Fixed link is link number 1, crank is link number 2, connecting rod link number 3, and piston is link number 4. Now in this, there are 4 turning pairs. P1 is the turning pair between link number 1 and 2. P2 is the turning pair between links 2 and 3. And P3 is the turning pair between links 3 and 4. And P4 is the sliding pair between link number 1 and 4. Now for pair P1, which is a turning pair, degree of freedom of this turning pair are 1. Since it is a pin joint, it has only pure turning motion. So degrees of freedom are 1. Take pair number 4, which is a sliding pair between link number 1 and 4. So this sliding pair also has 1 degree of freedom because the motion is pure sliding, or motion is pure translation in horizontal direction. Now if you want to define the mobility of this mechanism, look at this. Number of independent input parameters that are to be controlled so that the mechanism takes a definite position. If we consider the crank as the input member and theta as the instantaneous displacement of crank with respect to IDC, now the value of theta is sufficient to define the position of piston at any instant of crank rotation. Knowing the value of theta, we can predict the displacement of piston S. So mobility of slider crank mechanism is 1 because only one coordinate theta is required to define the position of any link in a mechanism. The next, we will see how to determine the degrees of freedom of planar mechanisms. First of all, we will go through the Sketchbox criteria. Sketchbox criteria to find out degrees of freedom. Now degrees of freedom of a mechanism in space can be obtained as below. Like this, degrees of freedom equals to 6 minus number of constraints. 6 minus number of constraints in space. If you consider a mechanism in space, the total number of degrees of freedom will be 6 minus whatever number of constraints we are applying to the mechanism. So let us suppose that your mechanism consists of L number of links. So number of movable links in a mechanism are L minus 1, because to obtain the mechanism from a kinematic chain, we always fix one link. So total movable links in a mechanism consisting of L number of links become L minus 1. Now degrees of freedom of L minus 1 movable links equals to 6 L minus 1 minus number of constraints. If L minus 1 links are movable, total degrees of freedom will be 6 into L minus 1 minus number of constraints will give the degrees of freedom of the mechanism. Now to build a mechanism, if we introduce P1 number of pairs having 1 degree of freedom in a mechanism, this P1 number of pairs, each P1 pair will impose 5 constraints or 5 restraints. How? Let us take an example. Say we have one fixed link in space, and if we attach link number 2 to this link number 1 which is fixed using a turning pair. Now before attaching link number 2 to link number 1, link number 2 was having 6 degrees of freedom because it can translate along 3 directions as well as it can rotate about those 3 directions. So it has 3 degrees of freedom. But after connecting this link to a fixed link in space, degrees of freedom are reduced by 5 because now this link can only rotate with respect to link number 1. And this has happened because of introducing this turning pair which is having 1 degree of freedom. So what we can conclude that if we introduce a 1 degree of freedom pair in a mechanism, it will impose 5 number of restraints. So degrees of freedom is equals to 6L minus 1. So if we introduce P1 number of pairs having 1 degree of freedom, so total number of restraints imposed will be 5P1. So minus 5P1. Now if you introduce P2 number of pairs having 2 degrees of freedom in a mechanism, each pair will impose 4 number of constraints. So total constraints will be 4P2. So minus 4P2. Now if we add P3 number of pairs having 3 degrees of freedom in a mechanism, each pair will impose 3 constraints. So total constraints imposed by P3 number of pairs are 3P3. Similarly, 2P4 minus P5. We cannot move beyond this because a mechanism cannot have 0 degrees of freedom. This equation is called as Sketchbox Criteria. This is called as Sketchbox Criteria, and this is used to determine degrees of freedom of spatial mechanisms, means mechanisms having 3-dimensional motion paths. Mechanisms having 3-dimensional motion paths. Now let us reduce this equation for planar mechanisms. For a planar mechanism or a rigid body in 2-dimensional plane, it can translate along x direction, it can translate along y direction, as well as it can rotate about z axis. So a rigid body in 2-dimensional plane have 3 degrees of freedom. For a mechanism in 2-dimensional plane, we call such mechanisms as planar mechanisms. So for planar mechanisms, if there are L number of links in a mechanism, total number of movable links will be L minus 1. So degree of freedom of this L minus 1 movable links in a plane will be 3L minus 1 minus twice P1 are the number of constraints imposed by P1 number of pairs having 1 degree of freedom, and 1P2 are the number of constraints imposed by number of pairs having 2 degrees of freedom. This equation is called as Grubler's criteria. This is used to determine degrees of freedom of planar mechanisms. This is used to determine degrees of freedom of planar mechanisms. So we have defined the degrees of freedom as a number of independent motions a body can have. We have defined the mobility as independent input parameters that are required to be controlled so that the mechanism takes a definite position. We have seen an example of slide recurrent chain. We have derived the equation for degrees of freedom in space. We have derived the equation for degrees of freedom for planar mechanisms, which was F equals to 3L minus 1 minus twice P1 minus P2, where L stands for total number of links in a mechanism. Total number of links. P1 is the number of pairs in a mechanism having 1 degree of freedom, or total number of lower pairs. Total number of lower pairs, or we can define P1 as total number of binary joints. Total number of binary joints in a mechanism plus the number of sliding pairs. The number of sliding pairs. And P2 stands for number of pairs having 2 degrees of freedom, or total number of higher pairs. Total number of higher pairs. So for determining P1, we can directly use this. Instead of finding the total number of lower pairs, we can use this. Count the number of binary joints and add total number of sliding pairs to it. So we'll get the value of P1. So this is the Grubler's criteria. Now we'll solve some numericals. So let us apply the Grubler's criteria for some simple mechanisms. Number 1, this consists of 3 number of links. So we'll number the links 1, 2, 3. So L equals to 3. We'll count the total number of binary joints. So P1 equals to 1, 2, 3. So F equals to 3. L minus 1 minus twice P1 minus P2. This gives 3, 3 minus 1 minus twice 3. So 6 minus 6 is equals to 0. So degrees of freedom are 0. F equals to 0. Now for such mechanisms whose degrees of freedom are 0, we will call such mechanisms as structures, because relative motion between the links is not possible. Take example number 2, having 4 links. So we'll number the links. Link number 1, link number 2, 3 and 4. So L equals to 4. Number of binary joints 1, 2, 3 and 4. So number of binary joints are 4. So just recall that binary joint is a joint where two links are connected. Okay, so F equals to 3L minus 1 minus twice P1 minus P2. We get 3. 4 minus 1 is 3. Minus 2 into 4. Higher pairs are 0. So 6 minus 9 minus 8 is 1. So degree of freedom is 1. For such mechanisms whose degrees of freedom or degree of freedom are 1, we call such mechanism as constraint mechanisms or constraint kinematic chains. We call such chain as constraint kinematic chain or constraint mechanism. Now example number 3, that is increase number of links by 1. 1, 2, 3, 4, 5 links. We'll count the total number of binary joints or lower pairs. 1, 2, 3, 4 and 5. So L equals to 5, P1 equals to 5, P2 is 0. So degrees of freedom equals to 3. L minus 1 is 4 minus twice P1. So 12 minus 10 equals to 2. So degree of freedom of this mechanism having 5 number of links is 2. For such mechanisms whose degree of freedom are greater than 1, these mechanisms or kinematic chains are called as unconstrained kinematic chains or unconstrained mechanisms. We call these mechanisms as unconstrained mechanisms. The next example number 4. One, 2, 3, 4 and link number 5. This link is fixed. So link number 1, link number 2, link number 3, link number 4 and this is link number 5. So total links are 5. P1 number of binary joints 1, 2, 3, 4, 5, 6. 6 number of binary joints are there because these are ternary joints where 3 links are connected. So each ternary joint corresponds to 2 binary joints. So 1, 2, 3, 4, 5, 6 and number of higher pairs are 0. So degree of freedom F equals to 3L minus 1 minus twice P1 minus 0 equals to 12 minus 12 equals to 0. So this is again a structure. This is a structure. We'll take one more example. Example number 5. 4 links. Link number 5. Link number 6. 1, 2, 3, 4, 5 and 6. 6 number of links are there. So L equals to 6. Now we'll count the total number of binary joints plus sliding pairs. 3 links are connected, so ternary joint. 1 ternary joint corresponds to 2 binary joints. So 2, 2, 4, 5, 6, 7, 8 and higher pairs are 0. So degrees of freedom equals to 3 L minus 1 minus twice P1 minus P2. So 15 minus 16. F is minus 1. For such mechanisms whose degree of freedom is negative, we call such mechanisms as superstructures or indeterminate structure. Indeterminate structures. Because motion is highly impossible, or these are sometimes called as redundant structures. Redundant structures for those having negative degrees of freedom. So what we can conclude is that we can apply the Grubler's criteria to determine whether the given mechanism is the constrained kinematic chain or a structure or a superstructure or unconstrained mechanism. If degree of freedom is 1, the mechanism will be constrained. If degree of freedom is 0, we will call the mechanism as structure. If degree of freedom is negative, call the mechanism as superstructure. And if degree of freedom is greater than 1, we will call the mechanism as unconstrained mechanism. Now we will solve one more example on this. We'll solve one more example. So we'll count the number of links. 1, 2, 3, 4. So L equals to 4, P1. Total number of lower pairs are the pairs having 1 degree of freedom. It is the turning pair 1, 2, 3. Number of higher pairs 1. So degree of freedom equals to 3. L minus 1 minus twice P1 minus P2. This is equals to 3. 4 minus 1 3 minus twice 3 minus 1. 9 minus 6 minus 1 is 2. So degree of freedom of this mechanism are 2. Let us take one more example. The mechanism involving a ternary link. This is a ternary link. Two binary links. One more binary link connected to slider. So we'll count the links. Fixed link is always link number 1. Link number 2, 3. This is link number 4, ternary link. Link number 5 and slider is link number 6. So L equals to 6. P1, total number of binary joints plus sliding pairs. So total number of binary joints, this is 1. So we'll start from here. 1, 2, 3, 4, 5, 6 plus 1 sliding pair 7. Now let us do the calculation. F equals to 3L minus 1 minus twice P1 minus P2 are 0. So 15 minus 14 we get degree of freedom as 1. So in this way you can apply the Grubler's criteria to find out degrees of freedom of planar mechanisms. Now let us have a look of degrees of freedom of different kinematic pairs. First of all, we'll take an example of sliding pair. In case of sliding pair, one element or one link slides relative to another link. So this is link number 1, this is link number 2. Link number 2 slides inside the link number 1. So number of motions executed by link 1 relative to link 2 is the translation motion in one direction only. So degree of freedom of sliding pair is 1. Now turning pair, shaft with collars at one end as well as another end rotating inside the bearing forms a turning pair. Now this shaft can only turn inside the bearing. So only single variable theta is sufficient to define the position of shaft, that is link number 1, with respect to bearing, that is link number 2. So degree of freedom of turning pair is 1. Next is the cylindrical pair, in which shaft, so link number 1, turns inside the bearing, or link number 2. Now in this case, in case of cylindrical pair, the shaft can rotate as well as it can slide inside the bearing, and both the variables theta and s are independent. Because we cannot exactly predict the amount by which the shaft will go inside the bearing when we rotate the shaft through a specific angle. So theta and s are independent, so both are counted as separate variables. So degree of freedom of cylindrical pair is 2. Now screw pair. In case of screw pair, one element in the form of screw or threads turns inside the another element. This is screw pair. Now in this, link number 1 will turn or rotate about its own axis as well as it goes inside the link number 2. But in this case, we can exactly predict the amount by which the screw will go inside the nut when you rotate the screw by some specific angle theta. So theta and s are dependent. Theta and s are dependent. This is very important example to understand the degree of freedom. Theta and s are dependent because we can predict the amount of s by knowing the amount of theta, or we can say that any one of these two variables, s or theta, is sufficient to define the position of screw inside the nut. So degree of freedom is 1 for screw pair, because we count theta and s as a single variable because both of them are dependent. And according to the definition of degrees of freedom, we have to count the independent variables, number of independent variables, to count the degrees of freedom. The next is the rolling pair. In case of rolling pair, one element rolls over the surface of another element. So rolling pair usually have 1 or 2 degrees of freedom. 1 degree of freedom corresponds to the rolling and another degree of freedom corresponds to the slip between the two elements. If slip is absent, we count degree of freedom as 1 for rolling pair. Next is spherical pair or ball and socket joint, in which one element turns inside the another element like this. This can rotate about x-axis, y-axis and z-axis. So ball and socket joint or spherical pair has 3 degrees of freedom, and all the 3 degrees are of rotation about x, y and z axis. Thank you.